So welcome to this talk on algorithmic trading using high-performance data processing in Python. Just a bit of background about myself. I'm a software engineer that works for a firm called Engineers Gate. We're an algorithmic trading fund, so our entire purpose is to build automated trading systems that predict where the stock market is going to go. So my time is split between building out our data processing infrastructure, so munging lots and lots of numerical data, as well as building out our real-time trading systems that actually execute the trades that we decide to make. So I'm a cross between Python and C++, and also a bit of a Rust enthusiast, but the majority of my time is spent on Python. So as we all know, Python is a hugely popular tool for data analysis. A JetBrains survey last year showed that data analysis is now as popular as web development in Python. So 50% of all use cases of all the survey developers were doing stuff with data as opposed to just, say, web applications. And why? Because Python is, first of all, suitable for research. It's high level and easy to use. It doesn't require advanced programming knowledge. So it enables researchers that aren't programmers full time to iterate on ideas very quickly. But it's also suitable for production. And this is where Python's edges over, say, R. So Python is a general purpose language that's useful outside of data analysis because you have a huge ecosystem of packages and tools for deploying production-ready systems. So you can take your research code and run it in production instantly without any changes. And that's basically its kind of core strength. So we want to be able to use the same code that researchers are using in research in production. The problem is that Python is really slow. This isn't exactly news. Any benchmark that you have of any natively compiled language shows that Python is significantly slower. So even heavily optimized Python code, pure Python code, is not as fast as, say, C. And this is bad for research because it means that your experimentation cycles are very slow. You can't iterate very fast because your experiments are taking so long to run. And it's bad for production because you can't run time-sensitive processing or computational tasks as well. So the solution to this is to use Python's data processing ecosystem. There's a wealth of packages in Python for processing data, analyzing, plotting data, and doing tons of stuff with it. We're just going to focus on NumPy. NumPy is essentially the heart of scientific computing in Python. It's a very low-level library that basically stores and operates on numerical data in C structures to avoid the slowness of Python. And it's a foundation of a lot of scientific computing packages like pandas, SciPy, scikit-learn, and so on. So our focus is to show how to use NumPy to process numerical data and exploring how NumPy uses vectorization to dramatically boost the performance of numerical code while keeping the productivity and the high-level ease of use that Python gives us. So what we're going to do is we're going to build an algorithmic trading strategy using stock price data. We're going to process that data in pure Python, and then we're going to speed up that processing in NumPy and vectorization. And then we're also going to speed up even more using another tool called numba to cover the cases that NumPy can't optimize for us. So the final solution will be 1,900 times faster than the original pure Python implementation. So let's do it. So suppose we're a developer and we're tired of working for a firm, we're tired of working for the man. We decide, you know what, loads of people are building automated trading strategies out there, let's do it ourselves. It turns out there's actually a decent amount of data online available for this. So we can find the price of 7,000 US stocks from 1962 until 2017. So this is a good base for us to start trying to build some sort of algorithm to do some trading. This data set, which you can find available in the links at the end of these slides, is a collection of CSV files, 7,000, one for each stock. And each file simply has two columns, the date and the close price. So when the US stock market closed for the day, this was the price on that date. So on the 7th of September 1984, Apple's price was 42 cents per share. So if you just plotted one of the files, you'd get something like this, which is pretty much what you'd expect from a stock price. Stock markets have generally been going up. So the dataset size is actually very small. It's only a gigabyte, which is very, very small, but we're going to be doing some pretty heavy computation on this data, which is where the slowness is going to come from. So our goal is to build a program that generates a list of trades to make. And what we're going to do is every single day, we're going to generate a single list of trades. So a single list of buy this amount of shares of a stock or sell this amount of shares of a stock. Disclaimer, this is a demo strategy. Please don't take this as real investment advice. You will lose money. But the positive note here is that this actual strategy does follow the high-level structure of many algorithmic trading strategies that run in real life. So for example, our firm, we use this type of high-level structure. So yeah. So what we're going to do is we're going to build this strategy by leveraging two fundamental behaviors about stock prices. The first one is that prices revert to the mean. So if you imagine any time series of some numerical data, a time series has a lot of noise in it. So as you see stock prices, they have this like jutter, so they go up and down, up and down, up and down. But also they may trend upwards or downwards. So stock might start rallying upwards over time, or it might end up going down because it's not a very successful business, for example. So what happens is you have this like price which fluctuates and then an overall trend. So in this case, if a stock was generally going up, it's not just going to be a straight line. It's instead going to be, it's going to go up and then down and up, and it's going to kind of vibrate around that sort of trend line. So we're going to leverage that insight into buying when the price is lower than the moving average, and then selling, say, a day or two later, because we expect or are predicting the price to revert back to the mean because it's below the mean. And we're going to do this by calculating the stock's daily return. So the daily return is just the change in price. So every single day, the change in price is the return on investment that you've gotten in that stock. This, for example, and that's just the price today minus the price yesterday, so just the change. So for example, we have a couple of weeks of pricing data for Apple. We see here how the price is like going down $1 or $2 and then going up $2 and so on. But this orange line is the moving average of the pricing changes of the return. And you see how it's hovering around 0. So what this indicates is that the trend so the actual price is fluctuating around some sort of central value because it goes back down but then always ends up going back up. So that's why you have this moving average of 0. So a mean reversion trading strategy is to buy or sell a stock when its returns exceed a certain threshold. There are many ways of defining threshold, very complex ways, but we're going to keep it simple in this case. So suppose we have $90,000 to trade with. This is the same pricing graph as before. Suppose we're just going to set a fixed threshold of $1. So if a price is reduced by more than $1 in a given day, we predict that it's going to bounce back up because it's gone down and it's going to revert back up to the mean. So we do that. So we're going to try and profit from this by buying at that point. So we say buy a bunch of shares. So suppose we buy 1,000 shares at $90 after the stock price goes down $2, and then we just hold it for one day. So we've got these 1,000 shares, and then no matter what happens, the next day we're just going to sell all those shares. We're going to liquidate our entire position. So if we sell the next day, because mean reversion dictates that eventually it will revert back to its mean, the hope is that you have this situation here where it's gone down $2 and then it's gone back up $2. Again, it's fluctuating around the same value. And by doing that in this specific example, we've made money because we've bought at 90,000. The shares have increased by $2 the next day because it's reverted back to the mean, and we've made $2,000. We can repeat this process again and again, hoping that this bet of it will revert back to the mean will give us profit each time. In reality, it doesn't always work. But the goal is that you're doing these trade pairs of buy and sells, and you're going to be right more times than you're wrong. So in this case, the total return on investment for our $90,000 is 2%, which isn't bad. So yeah, the goal is to make more right trades than wrong. But the problem is, what if the price doesn't revert back to the mean? So it's not always the case that a price will revert back to the mean. It could be that the stock's constantly going up because the company's announced they've had like triple the sales revenue than they expected in a given quarter. And suddenly now everyone's like, wants to buy that stock. And so if we tried to do mean reversion, we would lose money. So there's this concept of momentum where our price keeps increasing and increases accelerating value or decreases accelerating value. And if we try and use mean reversion, we'll lose money. So we try and leverage a second behavior, which is that stocks are correlated. So for example, Apple and Amazon, this is a plot of the price of Apple and Amazon over a given period of time. Blue is Apple, orange is Amazon. They're both tech companies, they're both in a similar industry, and this typically means they're quite correlated. So whenever Apple goes up, you find that the blue time series, which is Apple, goes up, the orange time series also goes up and down in similar ways. And similarly, Apple is actually correlated with the whole US stock market. So if the whole stock market goes down, or Apple goes down, generally the whole stock market goes down, and vice versa. So the goal is to try and use this knowledge of which stocks are correlated with each other to avoid trading during momentum phases, and only use mean reversion when the stocks are hovering around the same price. not when there's like fundamental changes in the market. For example, Apple's tripled its earnings or whatever, so people are buying more and it's worth more than the company is now. So I can't go into detail just for time purposes on exactly how we combine these two together, but basically what you need to understand is that we have 7,000 stocks and we compute 7,000 returns time series, the changes in price. We combine for each stock, we combine its returns time series with how it's correlated with all the other 7,000 stocks in the US stock market, and then we merge it into this adjusted, unexplained stock returns time series. And we apply mean reversion to this. Now, the unexplained stock returns represents movements in stock price that we can't explain. So, for example, if the whole US stock market is going up and Apple goes up, we can explain that. Or if all tech companies are going up and Apple's going up, then we can explain why it's going up. So we don't want to apply mean reversion because we're not sure if it's noise and it will just revert back down again. So yeah, as a concrete example, if Apple decreases in price, but other tech companies don't, we can't explain the decrease because nothing else has happened in the market, it seems, to explain why Apple has gone down. So we just assume it's noise and it's gone down, but will come back up again. And this is the hardest step. It typically involves the most basic method involves two techniques called principal components analysis and linear regression. But again, we can't cover these in detail here. The purpose of this is really to talk about how to take this algorithm and make it fast. So if we consider a pure Python implementation of this algorithm, to recap, essentially what we're doing is every weekday, just before the US stock market closes, we calculate each stock, again, the 7,000, each stock's daily returns for the past year. We calculate the correlations between each of these 7,000 returns time series, and then we use them to decide how much, doing this combination step, to get the unexplained stock returns and use that to decide how much to buy and sell of each stock. We buy and sell the decided stocks, and then we only wait one day, we always wait one day, and then we get rid of the stocks, so we sell them. Again, that's kind of what makes this strategy fairly simple. So we want to simulate how much money we would have made. So typically when you're building these algorithms, you run a back test to simulate how much money you would have made in the past. And we already have pricing data to do this, so we're able to actually do this with this specific example. So we're going to simulate from 1990 to the end of the data set, which is 2017, and we're going to see how well we perform. If we there's a pure Python implementation of the strategy I wrote. I ran the code, and what we get is essentially this. So initially, from 1990 to 2001, we're making some pretty good money. So year on year, we're making about 3 or 4% returns, which is pretty good. And so we overall end up making about 16%. However, as time goes on, we stop making money. So from 2001 onwards, we see that actually our cumulative returns, so we've earned about 3 or 4% each year, we get to about 16%, and then it just kind of divers and goes down a bit and never recovers, never gets any higher. So what this means is, if you kind of look at the year-on-year returns, in recent years, it's not very good. So really, you wouldn't actually use this algorithm now, because it was good in the past, and it's not good anymore. And by the way, if you're interested in knowing why this often happens, it's because algorithmic trading only really started to become really big in the early noughties, and so suddenly it became a lot harder. Like in the 90s, it was really easy to build automated trading strategies because no one was doing it, whereas now it's a lot harder. So our first attempt at an automated trading strategy failed. Not entirely surprising, because this stuff is really, really hard to get right. The problem here is that if I actually ran that simulation on the pure Python implementation that I wrote, it would have taken 3 years to compute. And these long simulations, even if it wasn't just 3 years and it was 3 days, that's a really, really long time. Long simulations are a huge problem. Strategies always require massive amounts of tuning and experimentation, and pretty much any kind of number crunching or data science project you're working on is going to require the same sort of quick iterations. So these types of long simulations are actually not acceptable. It needs to run fast. So what went wrong? Well, 3 steps in this process are computationally heavy. This return step, where we calculate each stock's daily returns. The correlation step, where we calculate how each stock is correlated to other stocks. And the decision step, where we use correlations and the returns and combine them. Now, to put it in kind of more concrete terms, I calculated the number of raw operations that are required to run this simulation with this pricing data. When I define an operation as like an addition, subtraction, multiplication. And in total, the total number of operations that need to run is about 200 trillion, which is a lot of operations. And when we break this down into how long it would have actually taken to run the full simulation in pure Python, we see this first step takes half a day, and then the others increasingly take significantly longer, which of course is unacceptable. Now, I'm not going to go into too much detail into why Python is so slow. I think most of you probably understand the reasons. It's not built for performance, and that's totally fine. But just to kind of give a quick recap on why Python is so slow with doing these types of numerical computations, the first is that it's dynamically typed. So the Python interpreter doesn't know the types of variables in advance, which means that in C, if you're adding two integers together, that's one instruction. Maybe in two instructions if you're doing like a load or something. But in Python, you always have to do all this extra type checking. So even simple operations, you have a 2-3 times slowdown minimum. More instructions are needed for basically any operation. And that's the primary reason why Python is slower than compiled languages, particularly native languages. The second reason is that it's interpreted and not compiled. Compilers are able to optimize code in advance. So if you have a compiler that knows exactly what your program can do, it can do very, very smart optimizations to make sure that it's fast. And the third reason is fragmented memory access. So if you consider an array of numbers, suppose it's our stock prices, in C, for example, you have this contiguous block of memory. There's no extra memory overhead. You just have integer, 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 all in a row. Whereas in Python, because a Python list can contain any type, then it means that actually it's a list of pointers. So what actually happens is you have this level of indirection where your list is just a list of memory addresses, and then you kind of move to where the Python object, it could be an integer, it could be a struct, it could be a class, it could be whatever. But you have that extra hop, and that kills cache performance. So suddenly all the optimizations that the CPU can do around caching data doesn't work. So how can we do better? So this is where we enter NumPy. So NumPy, as I mentioned, is the fundamental package for high-performance computing in Python. Many libraries and frameworks are built on top of it. And essentially what it offers is a class, a Python class, for representing multi-dimensional arrays. And it provides routines for performing very quick operations on these arrays. It also provides efficient loading and saving of numerical data on disk, CSV included, which is useful for this specific example, but even also more efficient binary formats like HDF5, which can be very useful for certain use cases. So we look at this multi-dimensional array type. This is numpy.ndArray, and this is the class that encapsulates the n-dimensional array storage. These are fixed size. You cannot change the size without creating a new array, and elements must be of the same type. So to give you an example, we can create an array, which is just a range of numbers increasing in sequence using np.arange. So we say np.arange 9, type is floats, float64, so doubles. And when you print it out, you just get this simple array of 9 numbers. Now what's important here is to understand how NumPy actually represents this data under the hood. So what's actually happening with this is a NumPy array is actually just consists of these parameters on the left. So the first is a pointer to some data buffer. So this is some contiguous block of memory that stores all the data that that array stores. Then you have the data type, which is float64 in this case. And the interesting parts are these shapes and stride parameters, which allow you to do lots of very interesting things. So here the shape is obvious, so it's a 9-sized array, or it's got 9 floats, so the shape is 9. And the stride indicates and tells NumPy how many bytes along this buffer you need to move in order to get to the next element. And this allows you to do very interesting things. So for example, suppose that this array was 10 million or 100 million numbers, and you wanted to reshape this array into a 2x2 matrix. You can do this using the reshape function. We say, here we're turning this 9-sized array into a 3x3 matrix, but we're not doing any copying. We're just doing a.reshape, and all that changes are the shape and stride parameters. The data buffer remains entirely unchanged. So we just change shape to 3.3 and strides to 24, which is because you need to move 24 bytes to get to the next row, and then 8 bytes to get to the next column. 8 bytes again because we're storing float64s. So you can even do things like slicing one dimension out. So you can say pick the first 2 columns, but not the third column. And again, no copying is happening here. All it's doing is changing the shape parameter, and NumPy knows how to interact and use the data. So the key here is that reshaping or slicing creates a view. No copies are made. And with these attributes, such as the contiguous data buffer, as well as these efficient transformation operations you can do with no copies, you get a lot of performance benefits. So again, you avoid cache misses because your data is stored contiguously. There's no copies for common operations. And the point is, NumPy has all these really, really heavily optimized routines for operating on these data buffers for you. So just as a basic benchmark, if we were to add 10 million numbers, in pure Python, we're going to exclude the sum function because that's implemented in C. So let's just pretend that this is, we're just actually trying to do some more complex computation in Python. Then what we're going to do is create two lists of 10 million numbers, and then we're just going to use a list comprehension to add them together and create a third list. In NumPy, we create two NumPy arrays, np.arange, and there's two ways we can do this. We could either create a separate new array, or initialize all to zeros, and then use a Python loop to iterate through the two NumPy arrays and like calculate the sum and then insert it into the array. Or we can just use the built-in NumPy operator. And when we time this, the results are quite interesting. So Python, this is on this MacBook, well, the MacBook that didn't work, but this is basically timed on my MacBook, but this took a second on Python, pure Python. Interestingly, NumPy was a lot slower with the looped approach, and NumPy built-in was 0.03 seconds. So we got 36 times speed up by using NumPy, using the built-in operator, but the NumPy with loops was actually the slowest. It took almost 4 times as long. And this is quite important to understand. So NumPy is not some panacea that will just fix all your problems. When you explicitly loop over NumPy arrays, what's actually going on is that every single time you do an addition, or even you're retrieving an element from the array, you're moving down to the NumPy C level, you're going into the data buffer for that NumPy array, and you're moving that back up into the Python layer, which results in a copy. So what's actually happening here is you're copying every single time that you're retrieving an element from the NumPy array. So we've got a lot of copies, we've got a lot of inefficient code because every single access of any of those arrays, which happens 10 million times, 30 million if you include all 3 arrays, is occurring. Whereas when you use the built-in operator, you're actually just using one Python operation, if you will, which is the addition, which is just a function call, and then all the rest of the code and all the calculations are happening in the optimized NumPy level, and that's the important part. So the key here is you keep things in NumPy. You don't loop through NumPy arrays, you move all the computation down to NumPy, otherwise you're not really going to get the advantages of NumPy. There's other problems here. So for example, that's all well and good if you're adding 2 arrays that are the same size, but if you're adding, say, 1 to an array of 10 million numbers, it seems like if you wanted to utilize the addition operator, you would need to create another array of all 1s and then add the 2 together. So that would obviously be very bad, because if you wanted to add 1 to 10 million numbers, you don't want to create a separate array of 10 million numbers just so you can do this NumPy addition. Then you're doing 10 million copies and you're not really getting any of the benefit. So NumPy offers a feature called broadcasting, which allows you to apply smaller arrays to larger arrays without copying. So you can actually just add, say, a 1 to an array of 10 million numbers, or 9 in this case, and it will know how to broadcast to all of them without any copies. Similarly, you can do the same with, if you're multiplying a vector by a matrix, you can broadcast that vector onto the matrix, which allows you to do operations on different sized arrays without needing copies. So when we use NumPy for the trading simulation, I'd like to show you just how to use it for this first step, the return step. So this step is all about calculating each stock's daily returns for the past year. And what we're using to define return in this case is not absolute return. So we're not saying we gained $2 or lost $2. Instead, we're using relative percentage return. So just the price, we got 2% return or minus 2% return. And we do that by just getting to today's price, subtracting yesterday's price, and then dividing by yesterday's price. So to give you a concrete example, if we wanted to compute the return of the 2nd of August, 2017 for Apple, we just take that price, 155, minus it by 138, divide it by 148, sorry, divide it by 148, and then we get a percentage value. So we got a 4.7 return if we were to buy it at 148 and then sell it at 155. And we need to calculate this return for all stocks and all days of the simulation. So this is roughly about 7,000 by 8,000 values. So we could use a nested for loop. We could just say for stock in stocks, for date and dates in the simulation, calculate the return by taking the today's price minus yesterday's divided by yesterday's. But as we know, that's slow. These types of explicit loops in Python are very slow because there's lots of copies and generally slow operations because you need to do more instructions in the Python level. So instead what we want to do is use NumPy to compute the returns. We want to pack all the stock prices for all the dates into a single dense NumPy matrix, and then perform all the book operations on that matrix to keep the computation in C. So for example, this is what it might look like. So we have a 2x2 NumPy array. Not 2x2, sorry, we have a two-dimensional NumPy array where the first dimension is the dates and the second dimension is the stocks. So these are like stocks, ALPL is Apple, for example. So here you're just packing all the historical prices for all the stocks in a single two-dimensional array. And what we want to do is take this and then calculate the stock return matrix. So this is the prices at each date. And what we want to change it to is the percentage return on that date. So, which is basically the percentage change in price. So on the 9th of November 2017, Apple AAPL reduced in price by 0.2%. So to calculate one of these cells, you simply take, in the returns matrix, you simply take the two cells in the pricing matrix on the same day and the previous day, and then that's essentially how you calculate it. But again, instead of manually calculating each of these cells one by using Python loops, we're going to use bulk matrix operations in NumPy. So if we take our prices matrix, then we shift it down once. So we have the prices on each day, and then we shift the prices down once. So we have the prices, the price of yesterday. So on the value for 175.61 in the middle of that, which is AAPL 9th of November, that's actually the price on the 8th. So we've shifted it down. Then we take our returns formula, which is today's price minus yesterday's prices divided by yesterday's prices, and we just substitute them with the full matrix. So we're not substituting it with one value of one cell, we're substituting the whole matrix in. And when we do that, we get our returns back. And the actual NumPy code to do this is very small. So we create a Python matrix, we initialize it to all zeros, we make the shape of the matrix the number of dates in our simulation, and then the number of stocks that we have available, which is about 7,000. We use those CSV files I mentioned earlier to populate the matrix. We then shift the prices down once to compute yesterday's prices, and then we just substitute in that returns formula the matrices. And that's all we do. So actually our code is a lot simpler because we haven't got like a million loops, but also at the same time, all this stuff is running in NumPy code. So the key here is that this one line of code is actually running hundreds of millions, if not billions of operations, but it's all happening in the C level as opposed to the Python level. So when we actually get the timing to that specific return step, we turn it from 642 minutes into 8 minutes. So we get a 79 times speed up. I don't have time to cover how exactly we use this for the correlation and decision steps, but basically we do the same thing. We pack everything in bulk matrices and then make sure all the computation is happening in C. And so the key takeaway here is that we express the data in vector matrix form, and this opens a whole new world of optimizations in NumPy and just in any kind of Python numerical computation library, because you want to avoid doing stuff in Python as much as possible when it comes to the number crunching parts. When we look at how using NumPy optimized the rest of the code, we get something like this. So we take it down from 3 years to 2.8 days. So we get a 395 times speed up. As you can see, we've taken stuff like this decision step down from 710 days to 2.61 days. Still not ideal, but we're at least getting somewhere. And to summarize why we're seeing such massive changes in speed, it really is just because of what I mentioned before, of NumPy has no extra memory overhead, there's minimal copying, it's cache friendly, and probably the most important, it's optimized in, the operations are executed in heavily optimized code, in C code. A lot of smart people have worked on this code, and it's not operating in the Python level, so it's a lot faster. However, there's also another aspect, which is called vectorization. So vectorization, in its most broadest sense, is the process of converting an algorithm from operating on a single value at a time to operating on a set of values at a time. So modern CPUs provide direct support for vector-based operations. So what this means is, instead of applying a single operation on a single value, single instruction, CPU instruction, sorry, to a single value, you can apply a single instruction to many values at the same time. So essentially you've got kind of like a mini parallelism. So as an example, if you wanted to add 1 to this array of 10 numbers, that would take 10 additions if you weren't using vectorization. With vectorization, what happens is in CPUs, you bundle many values in the same CPU register, and then you add those registers together with a single operation. So in this case, it's very common that you can usually fit 4 floating point values in a single vectorized register, which is called single instruction multiple data register, or SIMD. You can actually almost quarter the number of instructions required to actually compute that. So one important point here is that you may see vectorization used in very different ways. So if you're talking about native code or you're talking about CPUs, people refer to vectorization as what I just showed, applying single operations to multiple data items in parallel. Whereas in Python, typically people just tend to say your code is vectorized if you're expressing everything in vector matrix form. In other words, you're using NumPy and everything. You're not using explicit loops in NumPy in Python and stuff like that. So both of these involve making algorithms use vector matrix based computation instead of just naive iterative based computation. For the trading simulation, we actually got vectorization for free. So by expressing everything, for example, in that returns matrix, expressing everything in NumPy arrays, NumPy has already done the vectorization for us, so we haven't needed to do anything to get the benefit of it. However, this is not always the case. So you may have an algorithm that you can't vectorize, like it's impossible to vectorize, or it just might be incredibly difficult to vectorize, like non-trivial. So often you might want to make the pragmatic decision that rather than expressing everything in vectorized code, you can express it in iterative code instead, because it's easier to understand, it's easier to design, and again, not all algorithms are vectorizable. So, for example, here, our decision step is still really, really slow. So we can use a tool called numba to take this decision step, which has some non-vectorized parts in it, to speed it up dramatically. So again, the problem is that not all algorithms are vectorizable, so our solution is to compile that non-vectorizable code, Python code, into native machine instructions. And so numba is a library that basically allows you to decorate Python functions, and then numba will compile it to native machine code for you automatically on the fly. So there's a decorator called numba.jit. As an example, suppose we want to sum an array. So we just have an array of integers and we want to sum up all the values in that array. We just iterate through it and then we do plus equals. Again, we're assuming that sum isn't a function that exists. This could be something more complicated, but we're keeping it simple for the purposes of the talk. If we just do this, so if we just import numba.jit and then we do jit no Python equals true, what this tells numba is try to compile this Python code as native machine instructions. And the no Python equals true tells it if you cannot, if it's using special Python features, then raise an exception. So it won't let the code continue. And when we do this with this specific example, we get a massive speed up. So it takes 1.7 seconds in Python, and then using numba, it's 0.006 seconds. So we get a 270 times speed up just with adding one line of code to this function. Additionally, numba can also allow you to explicitly specify the types. So what's happening here is, in this previous example, numba, we didn't specify any types, but numba has to compile it to native machine code. And in native code, you need to know the types in advance. So numba actually infers the types for you based on what you pass it. Sometimes that inference can be inefficient, so you can actually explicitly specify the types yourself. So you can say, this function returns an integer and takes an array of integers as well. Now numba is not a magic thing that just you can just do @jit on everything and it's going to magically work. It's only really useful for these small, simple functions that have heavy loops, Python loops, that are doing numerical computation. When you use no Python equals true, you're very limited in what Python features you can actually use. You can't even just use classes outright. So it is really meant for very, very simple routines. When we use this for the trading simulation, I added @jit no Python equals true to all the functions, all the computation functions, and explicitly specify the types. What we get is, instead of 2.8 days, it takes 0.58 days. So we get a 1,900 times speed up in total. You see that the returns and correlation steps are the same because we've already run all that code in vectorized NumPy operations. So these two steps aren't affected at all, even though I added @jit, because there's nothing else to optimize or compile to native machine code. But the decision step, all those non-vectorized portions have been reduced. So the nutshell here is that you use vectorized NumPy code where possible, and you fall back to numba if your code can't be vectorized. So essentially, we've gone from taking 3 years, taking 2 days, or 14 hours, which is a pretty good speed up on a single MacBook Pro. And that's pretty much the talk. Just to recap, Python is great for research, but out of the box, Python is slow. There's increasing demands for faster real-time data processing. You might want to process large volumes of data or train complex machine learning models, but standard Python is not viable for many of these use cases. It's bad for research because it's slow and offers these very slow experimentation cycles, and it's bad for production because you can't run time-sensitive computational tasks. We can still use Python for both of these use cases by using Python's large ecosystem of Python packages. We keep all the computation in native code where possible. We vectorize using NumPy, and then for everything we can't vectorize or is difficult to vectorize, we use numba to optimize the rest. Now, if that isn't enough, you can parallelize. I mentioned this as like a final closing point because I think what a lot of people do is when they see something is slow, they immediately go to parallelize or distribute stuff across a compute cluster, which is great, but really all you're doing is you're throwing the problem over to DevOps. Because if you have something that runs really slowly and you just decide, oh, well, there's some embarrassingly parallel parts, split it up on a bunch of machines, then you've got to deal with all of the DevOps and distributed systems issues that happen when you're running multiple machines, or the setup. You could have a machine that just fails. Do you recover properly from that? And all these other different types of things. So I would encourage people to first see, when they have numerical computation code, to actually optimize it using these types of libraries first, like numba and numpy, as opposed to just immediately parallelizing. Just using numpy and numba alone can yield thousands of times speed up with relatively little effort. And yeah, that's the talk. Here's the link to the slides. And please get in touch if you have any questions, and I'll welcome any questions now.
Thanks, Alan. Can you hear me? Can you hear me? No. Yep. Okay. We just have time for one question. Donald, you're going to be around for the rest of the time, so you can approach him in the hallways. Would anybody like to ask a question? Yeah. Okay, great.
So throughout you used mostly simple mathematical operations, addition, subtraction, and a couple of divisions. Would this method be applicable to like sines, cosines, powers, roots, things like that, more complex mathematical operations?
Yes, so NumPy has most of those common types of complex transformations already. So it's, sin, cosine, powers, all that type of stuff, they have native routines for. So you still get to use that heavily optimized NumPy code because they've done the work for you to implement that, basically. Yeah. So all that stuff, they just have built-in stuff. One thing to note is that NumPy is inherently meant to be very lightweight and simple. So a lot of transformations you might not find in NumPy, but you often find in its sister package, SciPy. So SciPy offers just basically 100 times more common operations on NumPy arrays. So you would probably use that and fall back to that. Yeah. Cool.